Hello everyone, welcome to my topic circuits and networks. Today we are going to deal with single phase AC supply applied to RLC parallel network. So you can see in this two circuit diagrams whether resistor in series with inductor is connected parallel with capacitor or individually resistor, inductor and capacitor they are arranged in parallel, or you can have a multiple combinations under parallel network circuit. So in the last classes in last 10 classes of different single phase AC supply applied to series RLC network, we have seen the power calculations, the current calculations, and in today's class, we are going to see the parallel combination and their calculations. So you can see either you can have a network which can be arranged as parallel to AC in this form. ZA and ZB are known as the impedances, or in some cases, like in figure B, the arrangement can be made as ZA, ZB under AC supply. So you can see these kind of circuits or in these kind of circuits. So as I told you, ZA and ZB are the individual impedances. This impedance can be RLC in series or RC in series or LC in series, and the combination can be made into parallel. So when they are made in parallel for these two parallel circuits, the total impedance, like in the case of resistors, can be calculated as 1 by Z total is equal to 1 by ZA plus 1 by ZB, which will give you the total impedance value as ZA ZB by ZA plus ZB. So when you look at some examples, like in figure 2, you can see R1 in series with J omega L1. This is nothing but inductive reactance. The reactance it is taken in terms of inductor, where XL or XL1 can be treated as omega L1, where omega is the angular frequency. So these parallel combinations at these 2 points, when current enters into this, the current gets divided because it's a parallel circuit as I1 and I2, and then the current comes out. So if at all you need to estimate the impedance from the formula of Z parallel, that is ZA into ZB by ZA plus ZB. So here we have taken the impedance parameters in terms of real as well as the reactive component. So this is how the total impedance of the parallel circuit is estimated. In figure 3 you can see instead of J omega L2 it is minus J XC. So this XC represents the value of capacitive reactance. Just the values of inductive reactance and capacitive reactance, either they can give in this fashion or they can give in the form of inductors or capacitors in another way. For this, if at all you want to estimate the impedance, so this is how the impedance will be calculated. You can see R plus J XL multiplied to R minus J XC. Since the capacitance, that's why it is minus J XC total divided by the sum of the two impedances. Let us go with the practical problem where you have 230 volts 50 hertz supply and it is giving a current to this circuit. In one impedance you have 10 ohms and zero point 0.2 henries, and another impedance it is directly given as 40 microfarads. So like applying the formulas for inductive reactance, which is equal to 2 pi fl, substituting the value of f and l. So I'm going to get the value of inductive reactance as 62.83 ohms. Since it's an inductive reactance, that's why the unit is in ohms. Individual unit of inductor is Henry. Similarly, you can calculate the capacitance reactance, which is 1 by 2 pi fc. So 2 pi 50, it is given here as 40 microfarads. What we need to estimate? We need to estimate the power consumed. So in order to obtain the power, we should know what is the current and what is the power factor. For that, we are estimating all these values. So here the capacitive reactance is obtained as 79.57 ohms. See, ohms, it is again capacitive reactance. That is why it is the unit is ohms. Individual capacitor unit is farad. So estimate the value of impedance 1, which is a combination of 10 j omega L. So already omega L in conjugation with J, it is treated as inductive reactance whose value is 62.83 ohms. So that is how it is substituted in rectangular form. This is the representation of rectangular form. You can change it to polar form by taking the magnitude as under root of 10 square plus 62.83 square. Then you will get the impedance form, and the angle by which one component lead or lag with another component, that is voltage or current, will be obtained as theta is equal to tan inverse y by x, or the reactive component to the real component. So with this, the calculation is obtained to be 63.6 as the impedance magnitude at an angle 80.95 degrees. So this is the polar form of this impedance Z1. Similarly, you have capacitive reactance in the name of impedance 2. So that you can change it to the value of XC here as 79.57. So that is substituted here. And this rectangular form is changed to polar form like this, 79.57 at an angle minus 90 degrees. So once we obtain the impedances of individual branches, you can calculate the individual currents. This I is going to give the current I1 and I2. So I1 with the magnitude of impedance 1, which is 63.6 at an angle 80.95. So this will be giving you the value of current I1 as 3.615 at an angle minus 80.92 degrees. This denominator value, it is positive. When it goes to the numerator, it goes as minus 80.92. Here 230 volts is given. So it is understood that this is at 230 at an angle 0 degrees because it is taken as the reference value. So this polar can be changed to rectangular as 0.57 minus J 3.57, whole value as an impedance. So it is ohms. Now I can calculate the value of I2 as 230 divided by 79.57 at an angle minus 90, which will be obtaining as 2.89 at an angle 90 degrees. When this new denominator goes to the numerator, it becomes positive 90 degrees. 230 divided by 79.57 will be obtained as 2.89. So this is polar form and this is rectangular form. So once we obtain the value of current I1 and I2, we can easily obtain the value of total current, which is I here as 0.57 minus 0.68 J ohms. So this is the rectangular value and this is the polar value, which is 0.89 at an angle minus 50 degrees. So current unit is amperes. So once we calculate the current, let us see the power factor. Power factor it is obtained as cos of this angle value. So cos of minus 50 will be giving you the value as 0.64. So this is the power factor of the circuit. And finally, our requirement is power consumed by the circuit, whose formula is P is equal to VI cos phi. So substituting the values of V, which is 230, I, which is 0.89 or 0.88 I have taken here, with power factor 0.64, will roughly give you the value of power as 129.53 watts. So this is how we solve the parallel circuit problems. In order to understand in better way, let us go with another example. Here you can see individual resistor, inductor, capacitor, they are arranged in parallel and given to the supply 230 at an angle, 230 at 50 hertz. Again, we need to calculate the power. Why I am calculating only the power? Because when I am going to calculate the power, individually I am calculating or estimating the impedances, the total impedances, the total currents with individual branch currents, and then with the given voltage, with the obtained value of current, and with the power factor, I can estimate the power consumed. So substituting the value of XL as 2 by 50, 42. Here it is, you can see 42 milli indicates 10 to the power of minus 3. So this gives you the value of inductive reactance as 13.19 ohms. Then capacitive reactance, it is equal to 1 by 2 pi Fc. Substituting the value of F and C. C it is given, you can see 60 microfarads. Micro indicates 10 to the power of minus 6. So when this 10 to the power of minus 6 goes to the numerator, it becomes 10 to the power of plus 6. So this value divided by 2 pi 50 60 will give you the value as minus 53 J ohms. So this is again in the rectangular form. Once the values are estimated, just estimate the individual impedances. Impedance 1, because the first branch is having only 30 ohms, so 30 ohms. Second branch JXL, which is just we have obtained the value of XL as 13.19 J ohms, and Z3 as minus J XC, so minus 53 J ohms. So individual impedances are estimated. Then let us calculate the individual branch currents which are flowing in these directions. So I1 is equal to 230 at an angle 0 divided by 30. Since it's a resistance, it doesn't have any angle, because the resistance, the voltage and current are said to be in phase. So its value is 7.66 amperes. I2 230 at an angle 0 divided by 13.19 J. Just substitute the value by making small changes in your scientific calculator. First, you take this calculator, change it to complex mode, and substitute these values. You're going to get in rectangular form as minus 17.43 J, or you can change this to polar form again with the help of calculator as 17.43 at an angle minus 90 degrees. So this is the value of current in amperes for I2, another branch current. And third, the capacitance value, which we call as reactive capacitance, as minus 53 J. Substitute this value, I'm going to get the value of current here, the branch current, as 4.34 J. So this can be changed again to polar form. Why I have taken rectangular form and polar form? It is based upon the convenience on the given problem. You have ready-made answer in rectangular form and polar form. You can cross-check the results. Once the currents are obtained, that is the branch currents are obtained, we can calculate the total current. So I'm taking all the branch currents in rectangular form. So you can see we have the real value as 7.69 with the resistance. The second is the inductor, third is the capacitor. So because of that, the inductance and capacitance values in terms of the rectangular coordinates are taken. 17.443 plus 4.34. This minus and plus will give you the minus value as minus 13.09 J. So this is the total current in amperes, and the same rectangular form current is changed to the polar form as 15.17 at an angle minus 59.6 degrees. Now with this I have obtained the total current. So the power factor will be cos of the total power factor, which is minus 59.6. This is roughly 60 value. Cos 60 is approximately 0.5. So the power factor for this circuit is 0.5. Therefore the power consumed will be Vi cos phi. Just substitute the value of V and I, which is 15.17. You have to substitute the magnitude of total impedance. That's why we are taking the polar form here. And cos phi you have the value as 0.5. So with this, I'm going to get the total power consumed by this individual passive elements arranged in parallel to the supply to 30 volts at 50 Hz as 1744 watts. So this is how you solve the parallel circuit problems. I hope you like this video. Please like and share and subscribe to my channel, and please press the bell icon for the future notifications.